Hello.
Hello.
How are you today?
Really stressed about retrosynthesis.
Oh, restosynthesis. Yeah, I heard the today's lecture was like really confusing with the like bicyclic cyclohexane ring going backwards. Like I still need to see that lecture. Let me see if he posted it yet. Let's
Yeah,
see.
it's just when Pascal first talked about like the C2 limit or whatever, it was such a like I mean, he only introduced it on Tuesday. So, it's a little weird.
Yeah, like the for so this is how you can only use like at most two carbons.
Yeah, like that came out
Uh,
of nowhere.
yeah.
So, I'm at least I don't know how other people are feeling about it, but it's just very worrisome for
Yeah,
sure.
yeah, very like or they limit you to like and they restrict you to what kind of reagent reactant you could use for synthesis, like how many carbons maximum you could use for each reactant, right?
Yeah.
Yeah. Let's see. Did you have any questions to start with, or if not, we could try like doing some practice synthesis with that, like with the limits and restrictions.
Yeah, I was just hoping we could go over that and then also a comprehensive synthesis from old stuff if possible.
Yeah. Let's see. Right. Okay. Yeah. So let's see here. Let's try doing this reaction. Huh. Like a C2 example, was that an example of like the practice final? Um, was it during the lecture on Tuesday's lecture, the June 4th lecture?
Um, he did it on Tuesday and then also there was I think one question where it was like C2 limit or C6 limit or something like that on the midterm that he posted.
Let me see. Let's see. Um, oh, right. Devise a synthetic approach to the below molecule. The maximum allowable carbon fragment size for its starting materials is C2. So, for that type of synthesis problem, what that means is that the max amount of carbons your starting material has to start with and your reagents are 2 carbons long, right? Where in the reactant, we have to start with a molecule that's 2 carbons long, and then we have to introduce a reactant that's also 2 carbons long. So an example would be something like let's say he gives you this Wait, hello, can you hear me?
Yes.
Oh, okay. My MacBook is like crashing out right now. So I'm gonna use my iPad really quick. Okay. So, can you still see my screen?
Yeah.
Okay. So, a example synthesis where he restricts you on the max amount of carbons you could use is this right here, where let's say that he wants you to create this target molecule here, right? And the max carbon you could use for the reactants is 3 carbons long, or you could say C3, right? Where this is the product here, and we want to create this product using starting materials with at most 3 carbons or less, right? So to first think about this, we see that this is the carbonyl over here, and we could say that this is 1, 2, 3, 4, 5, right? Where you notice how there's a methyl group on carbon 4 right there, right? Oh wait, we're back. Okay, I'm back. So what do you notice about the group methyl group here relative to the carbonyl? Like, what position is it relative to the carbonyl group? Is it like alpha, beta, gamma, delta?
It's beta.
Yeah, it's beta, right? So this is alpha, beta. Where what reaction do you know that adds groups to a beta carbon to a carbonyl, right? Like, is it going to be a conjugate addition, 1,4 addition, 1,2 addition? Like, what reaction um will
Isn't
add?
it
Uh-huh.
isn't it 1,4?
Yeah, 1,4 addition, right? Where we could say that this came from an enone right there, where that beta carbon is the electrophile. So when we go backwards here, retrosynthesis, we could say that beta carbon was this beta carbon here that was the electrophile. And then you notice how we added an R group right there. That means that we want to use an organometallic reagent to add an R group to the beta position, right? But there are 2 possible electrophiles here from this enone. Which organometallic reagent do we want to use in order to attack the beta carbon here?
Would it be the Gilman?
Yeah, the Gilman one, the weaker organometallic one. It can't be the Grignard or MGBR or organolithium, because that would do a 1,2 addition, and we don't want that, right? So we are gonna use CH3 to CuLi, and second step H2SO4 or H3O plus for acid workup, right? And then what do you notice about this structure here? Like, what reaction can make an enone? This is chapter 18. There's a reaction that makes enones.
It's aldol condensation.
Right, aldol condensation. And do you remember how we can do retrosynthetic disconnection to predict the reactant? Like, how can we predict what's the nucleophile, and how can we predict what's the electrophile?
Isn't it 1,3 relationship?
Yeah, 1,3 relationship, where there was like an alcohol here, where you first locate the alpha carbon and beta carbon, and then you make a disconnection between them, right? when we make that disconnection, which atom is your nucleophile and which atom was the electrophile that made this enone?
The nucleophile would have been the alpha carbon.
Right, making the beta carbon the electrophile. Right. So when we make that disconnection and we go backwards here, we have this alpha carbon ketone, and then that makes this beta carbon here, right? That used to have a carbonyl because we know that was the electrophile, and then it has a methyl group and a hydrogen, right? So these are the starting materials here that would create that enone using NaOH, water, and heat, right? And this fulfills the thing because our starting material max amount of carbons is carbon 3, 1, 2, 3, like that, which checks out.
But then you said the reagents is also limited to 3 carbons, or is it just either the starting material or the reagent?
Yeah, the starting material or the reagent, right? This is
Okay.
not the reagent here because this is the product resulting from these starting materials here. And then from here, we just did the Gilman reagent to do a conjugate addition or 1,4 addition to get that group right there. Right. Let me give you another example here where, let's say, you are trying to create this, and then this is gonna be a big one. You are restricted to 7 carbons max, right? So any starting material you want has to have like no more than 7 carbons. You can have less, or you could have exactly 7.
Okay. So during lecture today, the head TA was saying like he counted the number of carbons total. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 total. Or no.
Oh,
No.
the longest chain.
Yeah, that's what I was counting, but
1, 2, 3, 4, 5, 6, 7, 8, 9, 9.
But do I count all the carbons or just the longest chain?
Wait, what was the reasoning why you're counting the longest chain?
I don't know. When he would say the limit of the carbons, and then he would also include the number of carbons total. So I don't know what the reason behind that was, but
Oh, so like for the last example here, like this is the longest chain, 1, 2, 3, 4, 5, and then the limit was 3. Right. So let's see.
Maybe it's like a way to figure out where you can cleave it, but I don't know.
Yeah, wait. I like to think of it more like the relationship between groups. Like, is it a 1,5 relationship, 1,3 relationship, or 1,1 relationship, right? Where we see that there are 2 carbonyls in that product with there, which has what kind of relationship with each other?
1, 2, 3, 4, 5.
Yeah, 1,5 dicarbonyl. And do you remember the reaction that makes a 1,5 dicarbonyl?
Michael addition.
Michael addition, right? And what was the nucleophile and electrophile of a Michael addition?
It would be an alpha beta unsaturated carbonyl with a regular or conjugated carbonyl with an unconjugated carbonyl.
Right. The alpha carbon of a carbonyl is the nucleophile. The alpha beta unsaturated carbonyl is the electrophile, where the beta carbon is specifically the electrophile. Right. Since this is symmetrical, we could say that this is the alpha carbon, that's the nucleophile, and we could say that this was the electrophile here.
Right.
When we do find that out, we can make that disconnection right there to give us that as the alpha carbon. And then since this is the electrophilic carbon here, we can say that this is the beta carbon of the alpha beta unsaturated carbonyl here, right? Where this is 1, 2, 3, 4, 5, 6, 7 carbons, which fits that restriction right there, right? But if he says he restricts you to 6 carbons instead, right? Like let's say your max was 6 carbons. This cannot be your starting material. How can we break this up even further to the starting material here, right? Think about what this functional group is and how we can break that up to make that functional group, right? Like what reaction makes that functional group, and then what are the nucleophiles and the electrophiles of that reaction?
So it's an alpha beta unsaturated, or it's a enone. So you would react it with the carbonyl portion, and then the double bond portion would be formaldehyde.
Right. Alpha beta. This is an enone where we know that enone comes from an aldol reaction where that alpha carbon there is the nucleophile, and then that dot beta carbon is the electrophile, which is going to be the formaldehyde. That's right. Right. Where that's the dot atom, which becomes formaldehyde, and then this is the nucleophile here that would react with this formaldehyde to create that under NaOH, water, and heat, right? Which now our starting materials are 6 carbons long. 1, 2, 3, 4, 5, 6 max, right? But if he says your max carbons is like 7, then you could say that that's the starting material. But if he says 6, you can't say that. You got to break it down even further, down into smaller starting material pieces.
Okay, so it's just, so when he says like C6 whatever, C whatever limit, it's just to tell you that whatever starting materials you have, it has to adhere to that number of carbons.
Yes, it can't exceed it. It could be lower, but it can't be higher. It could be lower, it could be the exact same, but it can't be higher.
Okay.
Right, just like this formaldehyde here, there's only 1 carbon, which adheres to that thing.
Oh, I see. Oh, so it can be less than or equal to the 6 carbons.
Yes. Yes, less than or equal to the 6 carbon.
Right.
Where we have 3 starting materials here.
Okay, that makes sense.
Yeah, nice. Now, do you want to try the comprehensive final review?
Yes.
Okay. Wait, let me try to turn on my MacBook really quick to see if it's like still good to join. Let's see. Okay, yeah. How do I? Okay. So that was the restriction of a synthesis where he could restrict you on the starting material you use, right? Because you can't use like a very bulky starting material if he restricts you down to 6 carbons. You just got to break it down further until you have like no more than the restricted amount. Okay, so let's see. Let's do the synthesis realm here. Let's do. Okay, so this is gonna be midterm 1 material here. And then after this, we'll do midterm 2 material synthesis. Okay, let's try this synthesis problem here.
Okay. Oh, oh wait, do we work on it for a little bit or can I?
Yeah.
Okay.
Yeah, you can see.
Um, so I was thinking
Mhm.
that because we end up with two carbonyls, that there's ozonolysis that happens
Yeah. Let's go backwards.
before. Mm-hmm.
Where, what is the reactant that made these two carbonyls here?
An alkene.
Yep, an alkene. Where we can say that when we do ozonolysis, we cut the alkene in half and put oxygens in the middle like that. Where let's say that this this alkene there, carbon there is alkene carbon right there, and then this alkene carbon here is this alkene carbon right here, right? Where that alkene carbon has two hydrogens, which are these two hydrogens here, and then that alkene hydrogen carbon has this hydrogen right there, right? Nice. And then how can we create that alkene, this alkene here, from this reactant here?
Wouldn't it be elimination?
Yes, elimination, but which type of elimination? Do we want the Zaitsev or Hoffman?
Oh, which one was it? Wasn't it whatever the more less substituted side was?
Yep, less substituted side, the Hoffman one. And if we want the less substituted side, we have to use a specific kind of base. What kind of base do we have to use to get the less substituted alkene?
More hindered.
Yeah, more hindered. So it could either be tributoxide or LDA. You can't use NaOH, or you can't use NaOR minus because that would create a double bond over here instead.
Mhm.
Right. Okay, so that was like midterm 1. Let's try to do midterm 2 here. Um let's see here. Okay, let's try this one here. Oh, wait. No. Let's not do that. Let's do yeah, let's do this. Let's do this one.
Okay. So in this case, wouldn't you sulfonate first?
Sulfonate, because you notice that these two groups are meta to each other, and you know the sulfonation group is a meta direct there,
Mm-hmm.
right? So okay. And then what happens after?
And then, oh wait.
Huh? Did you figure out the
Yeah.
mistake?
Yeah. Okay.
Okay, what
Um,
was the mistake? What happened?
so the only way to add a chain would be Friedel-Crafts,
Uh-huh.
but Friedel-Crafts can't
Uh-huh.
happen with a deactivated ring. So
Yeah. That's right. Uh-huh. This is deactivated. I was like, huh, you figured out. I'll just let you keep going, and then hopefully you'll catch yourself.
yeah. Okay.
Deactivated. Beetle crabs, no reaction. So the first thing is,
Uh, Friedel-Crafts alkylation.
wait, so is it going to be alkylation like this?
Uh, yes.
Right, so there is a problem here because think of the mechanism. Um, think about the leaving group leaving and then forming a carbocation here. What can this carbocation do in the intermediate?
Oh, wait, okay. Right, it has to rearrange, so it's
Uh-huh.
so the chlorine would have to be on the most substituted side instead?
Oh, right. So
Or
we don't want that because we want a primary carbon here where we could say that this came from a carbonyl. And what was the other Friedel-Crafts reaction?
acylation.
Acylation, right, right. So let's do acylation instead, where um this is the carbonyl group, and then this is the acyl group right there, and then AlCl3. That's the first step. Second step, acid breakup. We're going to add that acyl group right there. Right. Now, is this an EDG or EWG?
EWG.
Right. Uh-huh. And then what directing group is an EWG?
Meta.
Meta director, right? Which we see that this sulfonate group is meta to that group, so we could do sulfonation from here. Right. Sulfonation, bromination, nitration, halogenation, they all work with deactivated rings. The reactions that do not work with deactivated rings are Friedel-Crafts reactions.
Mhm.
Right. So we could still do sulfonation here. It could work on the deactivated rings though. Okay. And then there's one last step to go from here to here.
It wasn't H2PDC, was it?
Yep, it is. It is.
Okay.
H2 PDC. Uh-huh. Nice. Yeah. So the first step, Friedel-Crafts, acylation. Second step, sulfonation. And then third step, H2 PDC.
Mhm.
Yeah. Okay. Let's do the new material synthesis. Chapter 17, 18. Let's see. Let's do. Can we do? What can we do? What can we do? Okay. Now this is gonna use midterm one reaction as well. Like the synthesis has a midterm one reaction. Yeah, has midterm one reactions in there. But it does test a new chapter 18 concept. It has a 118, I mean it has a midterm like chapter 18 reaction. Right. You could go forward or backwards first, whichever one is easier.
Um, we'll see with seeing the alpha beta positions being conjugated and then an alcohol there, I'm thinking it was an alpha beta unsaturated carbonyl first.
Right? It came from that, where this is the new group here, an R group. And
Mhm.
we saw that R group attacked the carbonyl carbon. So what kind of reagent do we have to use to attack the carbonyl carbon?
Uh, Grignard.
Yeah, Grignard, right? Because we want the strong one, Grignard or organolithium. We can't use the Gilman because the Gilman would attack the beta carbon, A14 addition instead. So the Grignard we are going to use is 1, 2, 3, MgBr. Second step, acid workup to protonate the O minus. Right. So now we have to try to create this alpha beta unsaturated carbonyl from this thing here.
Oh.
It also has a like 118A reaction in here.
Is it like SN2? I don't, wait.
So let's say that this carbonyl here was is that carbon right there, right? Like this carbon here is that exact same carbon right there.
Mm-hmm.
Is this the Markovnikov or anti-Markovnikov position from the alkene?
Markovnikov.
Yep. How can we add an alcohol or an oxygen atom and that Markovnikov position?
It would be oxymercuration.
Yep. Oxymercuration, demercuration. Yeah. Which adds an alcohol on the Markovnikov position. And then how can we create a carbonyl from that secondary alcohol?
Oxidation.
Yeah, oxidation. So we could use PCC or Jones. It doesn't matter because it's a secondary alcohol. It won't like matter. It would matter if it was a primary alcohol though.
Mm-hmm.
Okay. Now we are trying to make this double bond right here from this here.
Oh, right. Wouldn't it be just base elimination?
Yeah, any base. It doesn't matter because there's no other beta hydrogen. Like that's the only hydrogen you could deprotonate. It's like
Mhm.
some kind of base grabs it, makes a double bond there, and it kicks out the leaving group. We could use. Oh wait, hold on. There's a problem here. Oh, okay, this is hard, more hard, like harder than usual. Because if we use a base, right, this hydrogen here,
Oh,
it
can make
would
an
like not make a double
enolate.
bond. Yeah, it would make the enolate. How can we like protect this carbonyl?
Acetylation.
Yep, acetylation. So we could do that diol with acid, which will protect that carbonyl with the cyclic acetal. And then we do that elimination step with the base to get that alkene that we want. And then from there, we deprotect it using. Okay, so this is a problem here. Because you know how we deprotect it with acid and water?
Mm-hmm.
It will deprotect that cyclic acetal to this carbonyl, but it would also react with the alkene. What would the acid and water do to the alkene?
Add an alcohol.
Yep, add an alcohol on the more subposition, but we don't want that. So we don't want to use a cyclic acetal protecting group. There's another protecting group that does not use acid and water to deprotect it. What is that other protecting group that we gotta use?
Sulfur.
Yeah, the thioacetal, the one with the sulfur, which is gonna be this here with the zinc chloride, right? And then do that E2 NaOH water base elimination, create that double bond. Okay, nice. And then from here to here, to deprotect that sulfur thioacetal, we don't use water and acid. We use this like weird thing, HgCl2, CaCl3, CH3CN, water, right? This would deprotect the thioacetal back into the carbonyl. This would not react with the alkene, right?
Would we, if we're say we have something like this, could we just write HgCl2 and be fine if it was just synthesis?
I think these two would be fine. These two together.
Okay, because he didn't provide, he just said that it was mercury
Oh,
2+ and then Zn 2+, I think. I
oh,
don't know if that's what I remember from my notes.
uh-huh. Um,
I only saw these reagents in Maria's stuff.
Oh yeah, these ones here, mirror stuff, fitness
Mm-hmm.
theory. I think depends on your TA. Like if your TA is lenient, then they'll give you points. But to be safe, I would put these two here.
Okay.
Yeah. Okay, so let me try to combine midterm one, midterm two, and the new material together for this one synthesis here. Let's see. Let me think about this really quick. Oh, okay. Let's try this one here. Oh wait, that's gonna be no. No. Okay, yeah. Let's do this. Let's do this one. There's multiple ways to start. Yeah, multiple correct ways to start this synthesis.
Is there a way when it's when it's like this, is it usually a safe assumption where to have where like the initial functional group is the same as the carbonyl, or is that
Mm.
is it do you just have to like feel it out based on your end product?
Yeah, you can say that the starting material is the carbonyl. Like if you say this is 1, 2, 3, 4, you can say that that is your 1, 2, 3, 4 right there. And then
Mm-hmm.
you can say that these are the new groups here, right?
Mm-hmm.
Or you could say this is your starting material here, 1, 2, 3, 4, and this is your starting material here, 1, 2, 3, 4, and then these are your new groups here.
Mm-hmm.
Right, you could do either way. And then whichever reactions you could think to make those things, and it works, then it will work for synthesis.
Okay.
Right? Whichever is easier, like that you could think of.
Well, first I was looking at the end product
Mhm.
and I saw that the uh e- ethyl substituent is 1,4 away like it's a 1,4,
Mm-hmm. Yeah,
uh,
the red
or
way, right? Or
yeah,
oh wait, hold
or
on.
wait. I was thinking it could have been a 1,4 edition.
Uh-huh. One for addition. So let's go backwards. Like instead of doing
Hmm.
that, you could just look at the end product right away and then see the relationship between them and then do that reaction right away. Where this is your 1, 2, 3, 4, and then there was a double bond between the 3 and 4 like that, right? For 1,4 addition, where this was the group that got attached to it. Um, what kind of reagent do we have to use to attach an R group to the beta carbon? A conjugate addition or a 1,4 addition?
1,4.
Yep, 1,4 addition. And then what reagent do we need to use to do this here?
Um, the Gilman.
Uh-huh. Right, the Gilman, where that's the R group, 2, and then copper, lithium, and then second step, acid workup. Right, that's the last step right there. Now we gotta try to create this from this here.
It would be, so again, it's an alpha beta. So when it's an alpha beta unsaturated carbonyl, it's always retrosynthetically an aldol condensation, right?
Yeah. Retrosynthetically outer condensation, right? Because alpha beta unsaturated carbonyl or an enone comes from an aldol condensation or dehydration.
Mhm.
Yeah. So if that's the case, we're gonna make that cut between the alpha and beta carbons, where what is the nucleophile here and what is the electrophile here?
The alpha position is the electro, no, nucleophile,
Uh-huh. And the
and the
beta
beta
carbon,
is the electrophile.
right. Uh-huh. And let's say that this was the beta carbon right here. That is the electrophile with the carbonyl right there, where it has 100, which is this 100 right here. Right. And then on this reagent, we're gonna put that acetone with base, water, and heat. Right? Because the base, water, and heat will generate the enolate ion here, making this alpha carbon the nucleophile, which will attack this electrophilic carbonyl carbon, pop the double bond onto the oxygen to make an O minus, and then that fully goes all the way down to like dehydration to create a double bond there between the star and dot, like that, and get rid of the carbonyl.
Mhm.
Right. Now we gotta figure out a way to make this aldehyde from this starting material here. Right, where let's say this is 1, 2, 3, 4, 1, 2, 3, 4, and then uh we want we want a carbonyl at carbon 4.
So first you would have to do elimination.
Mm-hmm. Right, and which type of elimination?
Um, is it Zaitsev with
Wait,
the,
that stuff would create the
oh,
moist stable
so Hoffman.
Hoffman, right, with the bulky base like LDA.
Hmm.
Nice.
And you would have to do
Mm-hmm.
hydroboration.
Yep, hydroversion and oxidation because we want the anti-Markovnikov alcohol.
Hmm.
Right, and then from here to here.
Uh, PCC.
Yeah, PCC, not Jones, because Jones would create a carboxylic acid, but we want the aldehyde there. Right. And from here, we do aldol dehydration by introducing this acetone with base and water to create that enone. And then from this enone, we do a 1,4 addition using the weak organometallic reagent Gilman.
Hmm.
Let's see. Oh, let me use this reaction here. I want to use this reaction in synthesis. Okay, let's do this one.
I see multiple ways this could go.
Mm-hmm.
But the one that's making sense to me right now is um alkyne to doing like a deprotonated terminal alkyne doing SN2 to that position,
Oh, I see.
like a nucleophilic attack, and then getting reduced by H2
Oh,
Lin-Lars. But I don't know if
oh yeah, 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 yeah. That is right. That's right. Like you're thinking of this way, right? Like 1, 2, 3, like that, and then 1, 2, 3, 1, 2, 3, and then that creates 2, 3, like that, and then H2 Lars.
Mhm.
Yeah, yeah, yeah. This works. This works. I wasn't thinking about that though, but that would work. Yeah. Think 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. That's the way we could do that. But what was the other way that you thought of?
um of some kind of other substitution, or I don't know, it's like throwing me off. That's the only thing that
Yeah, so
I
that
could
would
think of.
work.
Mhm.
Tian, do you know any reaction from chapter 17 that could create this? What kind of alkene is this? Is this an E alkene or a Z alkene here? Yep, it's an E alkene, right? Where what reaction in chapter 17 makes alkenes? It's a weird reaction. Uh right, and it could create either the E alkene or the Z alkene, depending on one of the reagents. Right? It starts with a W.
Isn't it the Wittig?
Yep, the Wittig reaction. Wittig reaction, right? And if we have this E alkene right here, we know the reagent. What are the reagents of the Wittig reaction? Like what reactants come together to make an alkene for Wittig? Like what are the names of the functional groups of the reactants?
Triphenylphosphorus.
Yep, triphenylphosphorus, and the other one is
Haloalkane?
carbonyl.
Oh,
Carbonyl.
carbonyl. Oh, okay.
Right, carbonyl. Where the triphenylphosphorus with the double bond alkene is an ylide. So for the Wittig reaction, the two reactants are um carbonyl plus an ylide, and that will make an alkene, right? But we could make this more specific by saying that if the ylide is unconjugated and that reacts with the carbonyl, that will create the Z alkene. If the ylide is conjugated, then that would create the E alkene when it reacts with the carbonyl, right? So let's make that cut between the alkene right there. And let's say that the two carbons of the alkenes are these right here. And let's say that's A and that's B. Since we have an E alkene, is carbon A or carbon B going to be the ylide if we want the E alkene?
What was the question again?
Right. So, is carbon A or carbon B of the alkene going to be the ylide group? Like which carbon is going to be the ylide? Which carbon is going to be the carbonyl to create this E alkene here? Right. Is carbon A going to be the carbonyl or the ylide? And is carbon B going to be the carbonyl or ylide? If we want the E alkene here.
Would it be A for carbonyl?
Right. So we have an E alkene, right, where we want the ylide to be conjugated. Um so A is conjugated, right? So we want A to be the ylide, right? Where like this would come from this reaction here, where the carbon A here has to be this ylide right here, reacting with this carbonyl right here. Right? Where this was the A carbon and this is the B carbon right here. Right? And for ylide reactions, we always combine the ylide carbon and the carbonyl carbon together, and then the oxygen and phosphorus with the triphenyl goes away, right? And the reason why I made this the ylide is because I want the ylide here to be conjugated to have resonance, because we want the E alkene. If this was the carbonyl instead and this was the ylide, right? The product that you would get is this right here, the Z alkene, right? Because this ylide here is unconjugated, which an unconjugated ylide gives you the Z alkene. But we want an E alkene, so we want this to be the ylide, what's conjugated. Right? And then to create that conjugated ylide from that thing, we do phosphorus triphenyl, and then second step of a strong base, right? Because the first step would first create this intermediate right here with the positive charged phosphorus. And then to create this double bond, we do some kind of strong base like N-butyllithium or NaH, right? Which will deprotonate that hydrogen and then make a double bond there to create the ylide right there, right? So your way was probably the easier way to do this synthesis, right? But then I wanted to use a Wittig reaction for synthesis, but you could have done it this way here.
So for Wittig, I just remember him saying that it's and now I forget what it was called, but he wasn't using unconjugated. It was like unstabilized versus
Ah,
stabilized.
yeah,
And he used
unstabilized. Uh-huh.
carbonyls on the illid and I don't know, maybe I was just not confused, but or sorry, not paying attention. So I'm
Uh-huh.
confused now. But is it better to know that if it's an E alkene in the end that you had a conjugated illid
Yeah, yeah,
and
right.
that sorry and so to figure that out like which side um is wait I'm like trying to verbalize this
Yeah, yeah,
in my
yeah.
um so because the benzene side would have been the conjugated side
hmm
that's of the alkene that's why you choose it
To be the ylide. hmm
right
Because this is the conjugated side, where I want the conjugated side to be the ylide side because we want the E alkene.
right could you do like another practice with Wittig again
Yeah.
'cause
Uh-huh. Yep, yep. Let's do that. Let's say we have Mm. Yeah, there we go. First, locate the alkene. If this is going to be coming from a Wittig reaction, we're going to cut that alkene in half. And then let's say this is the purple carbon and this is the green carbon, right? What kind of alkene is this here? E or Z?
Z.
Yeah, Z. If it's a Z alkene, what kind of ylid do we want? Conjugated or unconjugated?
Unconjugated.
Yep, unconjugated. Now, once we figure that out, we got to figure out which side is the unconjugated region.
The cyclopentane.
Right. Whereas that side here with the green carbon is the green carbon of the ylid, making the purple carbon here the carbon of the carbonyl, like that, right? Where when we react this together, that would create the Z alkene here. If we reversed the things, like making that green carbon the carbonyl, and then that purple carbon the ylid, then how would the product change?
The alkene would become the E
Yep.
alkene.
And it would look like this here, right? So yeah, right, because this is a unconjugated ylid giving you the Z. This is a conjugated ylid giving you the E. Like that.
Right.
Mhm.
So how do we, this is probably a stupid question, but how do we know if it's Wittig if the starting material isn't a carbonyl? Like if it shows up in synthesis, like would we just know? Because since it's so many,
So many reactions that you could do.
yeah, like it could
Your
like
way is probably the better way to do it. Like the
oh,
way that you
okay.
did here is probably better than the Wittig way.
Okay, so
I just wanted to make up a synthesis column using the Wittig, but that's
Mhm.
the worst way. Like I mean the like not the best way.
Right. So okay, because this would be like midterm 2 material with the thing that I proposed.
Uh-huh.
But
Oh, I found out one problem for your way. It's the last step.
oh, because it would be syn addition.
Uh-huh. And Lenoir's catalyst is a poison catalyst, which stops at what kind of alkene, cis or trans?
Is it cis?
Yeah, cis alkene, but we don't have a cis alkene here. We have a
Right.
trans alkene. And what reagent do you remember that makes the trans alkene from an alkyne?
Oh God. What alkyne?
I'll give you the name and the reagents might pop up. Dissolving metal reduction.
Oh, wait.
N.
Is it NaBH4 or
Oh,
no?
that's a reducing agent. It's gonna be sodium metal, like at least 2 EQ,
Oh,
and
yes,
then ammonia liquid.
that's right. It's
Uh-huh.
elemental sodium.
Yep, elemental sodium with that radical there or
Oh, yes.
there.
I completely
Yeah.
forgot about that.
Do you know the one that would fully reduce the alkyne down all the way down to an alkane if you wanted to do that?
Just H2PDC, right?
Right. H2PDC would go all the way down to the alkane. H2 Linoleum catalyst would go to the cis alkene, but we don't want that here. We want the trans alkene, which we use the sodium elemental and an ammonia liquid.
Mm-hmm.
Yeah. Mm-hmm. Yeah. Any other questions? Yeah. How do you pronounce your name again? Nare?
Nare, yeah.
Nare.
Mm-hmm.
Let's see. Are
Um,
you graduating this quarter?
no, I still have 2
Uh,
more years.
2 more
Yeah.
years. I see. I
Yeah.
see a picture. I see a stole there. I was like, oh, are you a senior or?
Oh no, that's my senior picture from when I graduated high school. That's why.
Oh, I see. I see.
Yeah.
I see.
Um,
Interesting. Yeah.
yeah. Uh, I was gonna ask about next quarter, but I know you're
Uh-huh.
graduating this year, right?
Yeah, I am. But I'll still be doing these office hours.
Oh, for free?
Yeah, for free.
Oh,
Yeah. These
okay.
office hours, it will be on the school page, the calendar link. Whenever there's a office hours link, then that's when I have it for free.
Okay.
Yeah.
Oh, that's golden,
Uh-huh.
honestly. You've been so helpful this whole time.
I'm glad. I'm glad.
Thank you very much.
Yeah, no
Um,
problem.
is it done or could
Uh,
we continue more or
yeah, the office hours is done, but I will send a message to Cannabis to everyone that I will be holding a final review session Sunday night, 8 to 10 p.m. Well,
okay,
that's like the last thing I do before your guys' final this quarter.
okay,
Uh-huh.
okay.
Yeah.
Thank you very much.
No problem. All right. See ya.
Bye.
Hey, Ryan.
Hello.
That was a long session, but the
It
final
kind of
school is coming
was,
up.
but I was just like waiting for. I mean, I wasn't really waiting. I was just watching at that point.
Like you're just watching, listening, getting prepared to learn this stuff when you take OChem.
Hmm.
Uh-huh. Right. How was your day today? Like, was it productive, unproductive? Did you follow the advice I gave you last night?
I'm like recording myself right now,
Uh-huh.
but I don't think it seems to be helping since I'm. Well, I haven't watched it yet, but I'm recording myself, so I'll be watching
Yeah,
it later.
that's good. That's good. Yeah. Yeah. I think I need to go sleep early tonight because I need to catch up on sleep.
Hmm.
Yeah.
What time did you go to sleep yesterday?
Really late. It was really bad. Like oh my gosh, it sounds so bad, like 3 or 4 a.m.
What the
But
frick?
I know. I need to sleep early like now, or, like as soon
Before a
as
test?
possible. Not for a test, just preparing stuff for like tutoring, like giving the notes and stuff like that, editing video and stuff like that. But I didn't need to do that, but that's why I'm gonna sleep early now.
Okay, go to sleep.
Yeah. Good night, Ryan. Good night.
Night.
I'll see you next office hours.
Yeah. Okay. Bye
Yeah.
bye.
Bye
Go to
bye.
sleep. Bye bye.
See ya.